part in the conference. So I want to talk about some dimensions for self-similar groups. So at first, let me start with the definition. What is a self-similar group? So we start with a finite alphabet, just a finite set. And then we consider X star, which is the free monoid generated by this finite set. So a set of words in this alphabet, including the empty word. And then a faithful action by permutations on this set is called self-similar if for every group element and for every word there is another group element such that if you apply the group elements to a word starting with V, so for every group element G and every word V, if you apply G to VW, you will act by G on the prefix on V, and then by this new element on the tail, so on the suffix. So in other words, the action of the group on the, so the group preserves the prefix relation, so it acts on, if two words have a common beginning, the images will have the common beginning of the same length. And then on the tail, the action is also an action by the same group, so by some other element of the same group. So you can use this formula to define an action on the infinite words. In fact, you just pass through the limit. So every self-similar group acts also on the set of all words infinite to the right. We also call this action self-similar. An equivalent algebraic approach is to look just at one letter, to look at the stabilizer of this letter, then this map, which describes the action on the tails from G to the new group element acting on the tail of words which start with X, will be a group homomorphism. And the stabilizer will be a subgroup of finite index. And if the action is transitive on X, then this homomorphism, which you call the virtual endomorphism, it determines the action. And if we insist that the action is faithful, then the group G might happen that the virtual endomorphism is defined on some bigger group, but then if you iterate it, take domains of iterations, take the core, intersect. Well, here I had to take not G but quotient by this subgroup. So the quotient by this intersection is the faithful action, faithful quotient. That's what we'll call it. Anyway, so the main definition is this, and I will give you a couple of examples in a minute. And we say that an action is contracting if there is a finite subset, which we call the nucleus, such that for every group element starting from some level length n, this group element which acts on the tails belongs to this finite set for all prefixes of length at least n. So we usually imagine this set X star, the set of words, as a tree. So you have the empty word on the root, finite words of length 1 on the first level under this root, then words of length 2 on the second level, so that prefix is a parent of every word below. And then if you have a group action, so an element acting on this rooted tree, then the action on every subtree going down will be also an element of the group. And so the contracting means that if you go deep enough in this tree and look how this group element acts on the subtrees deep enough, then all the actions that you see on these subtrees belong to a finite set. So eventually you see only a finite number of possible situations. And in terms of virtual endomorphism, this condition that you see only far too many possible behaviors is actually equivalent to the virtual endomorphism to contract the length of group elements. So this L of G, L of phi n of G is the length of group element with respect to some finite generating set. So asymptotically, the virtual endomorphism must contract the length, and that's where the word contracting comes from. So these two conditions are equivalent. It's not absolutely trivial, but that's not very hard. So here's an example. Here is an example of an action of the infinite cyclic group Z. So generated by one transformation A of words in the alphabet of two letters 0 and 1. And when you want to define an action of a cyclic group, you have to define just the action of the generator. So we define it like this. You have A of 0W is 1W. So if A gets a word which starts with 0, it just changes 0 to 1. If the word starts with 1, then it changes 1 to 0, and then it acts by A on the table. So you see that from this you get that A at 0 is identity. And here you see that A at 1 is A. So this is called the adding machine or odometer. It describes how you add 1 to a binary dyadic, but to a binary integer. If the integer ends with 0, you change 0 to 1. If it ends with 1, you change 1 to 0 and then carry. So add again 1 to the rest. And this is contracting with this nucleus equal to this set. That's something that you know from addition. If you take, if you add any number to another number, then eventually you will carry 1 only, or -1 if you subtract it. So eventually the thing that you carry is 1 or -1. Here is another variation of this. So we basically copy this rule, but replace A by B. So now if A gets 0, it changes it to 1. If it gets 1, it changes to 0. But then it acts by B, not by A. And B acts in this rule. It doesn't change the first letter. If it sees 0, it stops doing anything. If it sees 1, then it acts by A on the table. So these rules will define two transformations, A and B. So now if you see these rules, you can easily write down what is the value of A at any finite word and what is the value of B at any finite word. So you'll get an action of these two transformations, A and B. So you get two transformations. It's not hard to check that these two transformations are invertible, so are permutations. And so they will generate some group. And surprisingly, in this case, the group is very weird, very complicated. It's not a free group. It's not free. It's not a group which you will see before in classical group theory. So self-similar groups are rather complicated usually. And one of the goals of this talk is to show how contracting self-similar groups can be stratified by some dimension. So this group is also contracting, and the nucleus is this set of 7 elements: A1, A inverse, B inverse, AB inverse, B inverse. When did I start? So I know when I have to stop. It was 12. Okay. If a group is contracting, then you can associate with it something called contraction coefficients. So suppose we have a contracting self-similar group, and then let me denote by the P norm. So the usual notion of P norm in n-dimensional vector space. So you raise moduli of coordinates by p to the power p and add up and then take the pth root, and including the infinity norm, which is max. And so the LP contraction coefficient of the self-similar group is this number. Let me explain what it is. So you take all words of length n, take these what we call sections. So take the action on the tails for group elements, and then so you'll get a vector of dimension size of x to the power n. Take its LP norm. So take lengths of these group elements with respect to some generating set. So the vector of lengths will be some vector in some finite dimensional space. Take the p norm of that vector divided by the length of the original group element. Take this upper limit, lim sup, when length of group elements goes to infinity of the fraction. Take then the nth root of this and take the lim sup of this nth root. So in other words, you look how the LP norm is related, how the LP norm of lengths of these sections, of these restrictions, is scaled with respect to the length of the group element. So for example, if p is infinity, here you'll get maximum of length. So you get the longest section. If you take L1, you get the sum of lengths. Okay, so this number, because of this taking root, will not depend on the choice of the generating sets. So if you change the generating set, you'll change the length function, but this number will not depend on this length function. Also, it depends only on the associated virtual endomorphism. It doesn't depend on anything else. Okay, and one can show that the action is contracting if and only if the infinity norm, this number for infinity is less than 1. Okay, so suppose that the action is contracting, so the infinity contraction coefficient is less than 1. One can show that this function, which associates eta p to p, is a real valued function, is non-increasing, and it's continuous. That's another thing which you can prove. And we know that the group is contracting, so at infinity is less than 1. So we have some function which is non-increasing, and it goes to something which is less than 1 at infinity. So there will be some level, some moment, the last moment when it is greater or equal to 1. So let's be this critical value. So you take the infimum of the set of values of p for which this coefficient is less than 1. So this critical exponent has some implications algebraically. For example, you can show that the growth of the group is bounded by the exponent of n to the critical exponent. Of course, this proposition is silly and it's vacuous when PC is greater than 1. So this is interesting only when PC is less than 1. And there are such examples, for instance, the Grigorchuk group and other examples. This is basically a way how to show that these groups having sub-exponential growth. Another interesting fact is that this number gives you an estimate on the word problem. So there is, for every number greater than 1 and this critical exponent, there is an algorithm solving the word problem in this group G in the polynomial time equal to this number alpha. It would be also interesting to understand if this number is related to the Den function. Of course, these groups are usually infinitely presented, but there are some canonical finitely presented groups associated with them. And then the question may be, Den function is maximum of 2 and PC or something like that. I don't know exactly. Maybe 2 plus PC. That's an interesting problem to consider. Okay, so where these groups naturally appear, so they appear naturally as iterated monodromy groups. And I want to give the definition in a fair wide generality, but for lack of time, it will be a little bit compressed. So we start from 2 topological spaces, or more generally Orbi spaces, and we have 2 maps between them, going in the same direction, F and iota. And I think of iota as something approximately identity. So it imitates the identity map. So I'm thinking of it as a one map, but for some reason I separate 2 spaces, the space in 2 pieces, in two versions. And F is a finite degree covering map, and we assume that the spaces are connected. So this is something that we call covering correspondence, and it will define a virtual endomorphism of the fundamental group. Namely, if you have a loop in the space X, because F is a covering, you can lift it, and the set of loops which are lifted to loops will be a subgroup of finite index, because F is a finite degree covering map. So for a subgroup of finite index in the fundamental group, a lift will be a loop, so an element of the fundamental group of x1, and then you can push it back using iota to x. So lift and then lift by F and push forward by iota, that will be a virtual endomorphism of the fundamental group. And then we take iterations of this virtual endomorphism, domains of iterations, and then intersect everything, intersect conjugates, you get a normal subgroup and take the quotient. So the quotient is called the iterated monodromy group, and it will have a canonical class of self-similar actions. So that's how iterated monodromy groups appear, how self-similar groups appear. And if this covering correspondence is endowed with a metric such that the covering F is a local isometry and iota is a local contraction, then this iterated monodromy group will be a contracting self-similar group. So that's how contracting self-similar groups appear. Remember, I wanted iota to imitate the identity map. In that case, F becomes expanding. So it's a model of expanding maps, but if another way to formulate it, that iota is contracting and F is a local isometry. So we say that this pair of maps is a model of the group. It is related to something who know what it is. It's related to something called dual Moore diagrams, but I don't have time to talk about it. And every contracting self-similar group has a model, but you need X and X1 to be what is called Orbi spaces in general. Again, I don't have time to talk about it. It's not quite topological space, but it's also topological space with some groups attached to points, finite groups attached to points. Okay, if you have such a covering correspondence, you can sort of iterate it. At least you can talk about orbits. So a forward orbit is a finite or infinite sequence of points of x1 such that f of xn is iota of xn plus 1. Again, if you imagine that iota is identity, it just be the forward orbit. F of xn is xn plus 1. But here we have more freedom, so in choosing iota, so we have this condition. Now, if you take infinite sequences, we can take the space of all infinite sequences, is the space of the Cartesian Tikhonov power x1 raised to infinity. So it's a sum. If x1 is compact, x infinity is a compact topological space, and F induces the shift map on it. Consider the shift map on it. Call it F infinity. We get a dynamical system, a continuous map from x infinity to x infinity. And the important, the central theorem of the whole theory is that this dynamical system, so this space and this map, depends only on algebra. It depends only on this self-similar group, or the iterated monodromy group. If you know iterated monodromy group and the virtual endomorphism of it, so a purely algebraic object, you can recover this, what is called a limit dynamical system. So that doesn't matter what model you take, whatever model you take, this will this limit will be the same. So it will depend only on the iterated monodromy. And it's called the limit dynamical system of this iterated monodromy. So here's a synthetic way of constructing it. Suppose you have a contracting action. Consider the space of left infinite sequences. So sequences over the same alphabet but infinite to the left. And consider the following equivalence relation. You say that two such sequences are equivalent if and only if there exists a bounded sequence of group elements. Bounded means takes values inside a bounded subset, inside a finite subset, such that it moves the suffix to the suffix. So gn of xn up to x1 is equal to yn up to y1. And then take the quotient of this topological space by this equivalence relation. The equivalence relation is invariant under the map which removes the last letter, so under the shift. So that shift will induce a continuous self-map on this quotient space. And this is the limit dynamical system. So that's how you reconstruct this dynamical system, which was constructed using this pair of maps between topological spaces from the self-similar group. Okay, so the first notion of dimension is that topological dimension is related to the topological dimension of the limit space. So the fact is that the covering dimension, the usual Hausdorff topological dimension of the limit space, so the covering dimension, is equal to the lowest possible dimension of a contracting polyhedral model of this group. So if you can find a model where x and x1 are piecewise affine polyhedra, or even simplicial complexes, such that f is a local isometry, and actually you may assume that f is simplicial or cellular, and iota is piecewise affine and contracting, one has to pass to an iterate here, I forgot to tell. Then the lowest possible such model is, the dimension of such model is the same as the topological dimension of the limit space. So for example, the topological dimension is equal to 1 if and only if there is a model such that these two spaces are graphs, so graphs of groups. In high dimension, one has to use something called complexes of groups, to cover all. So here's an example. So the second example, the second of the two examples of self-similar groups, it has the following model. So here is space X, this is space X1, and A corresponds to this loop. So it's a bouquet of two loops. A is this loop, B is this loop, green is iota, black is covering map. So A is covered twice by this circle, so that's the inverse image of A. B is covered twice, once homomorphically by this loop, and once homomorphically by this loop. And then iota maps, and you take it as local isometry. So the lengths of curves are preserved by F. So in particular, this red circle is twice longer than this red circle. These two black circles are equal, have the same lengths as this circle. And iota maps this circle to this circle to this, and this circle is killed, so it's contracted to 1 point, So here the length will be contracted by square root of 2, or just multiplied by 0. So if the ratio of the lengths of these two circles is square root of 2. So this is a contracting model of this group. One can check that the iterated monodromy group is exactly given by these recursions. And what is the limit space? Well, we know that the limit space is the set of infinite sequences, infinite orbits. The sets of finite orbits can be built very easily by some inductive procedure, and they will be always graphs. So the x1 by itself is just the set of orbits of length 1, just points. This will be yes, this is x1. This will be the space of orbits of length 2. This is the space of orbits of length 3, 4, 5, 6, 7, 8. So the space of infinite orbits will be inverse limit of these topological spaces. And you see that these spaces are graphs, but they're one-dimensional. So the limit will have topological dimension 1, and it will be the Julia set of z square minus 4. So the space itself is very complicated, but it's a limit of graphs, so it's topological dimension 1. So as a corollary, we get that if you have a contracting self-similar group with one-dimensional connected limit space, then there is a contracting virtual endomorphism of a virtually free group such that the associated faithful quotient of H is G. So G will be contracting. You will see that it is contracting just looking at some virtually free group. And if the virtual endomorphism is onto, then this implies that the group G is either infinitely presented or isomorphic to infinite cyclic group or the infinity. So, or to the infinite dihedral group. It's an open question if finitely presented contracting groups are necessarily virtually nilpotent. So here they are virtually abelian. It's interesting that, so theory of self-similar groups, contracting groups, is with us for like 2 decades. And people have studied only one-dimensional groups. So there are many 2-dimensional, 3-dimensional, and so on examples. But in some sense, we don't have techniques to study them. We don't know anything about them. So that's one of the reasons why I wanted to separate, to classify, to grade these groups by dimensions, because by now we understand, we studied only one-dimensional examples. You can construct 2-dimensional, 3-dimensional examples, and so on, but we know nothing about them. So that's one of the reasons why it would be interesting. For instance, it would be interesting so here for one-dimensional case, you have these free groups from which you start studying these self-similar groups. What are the groups in 2-dimensional case? They will be some finitely presented groups, but what kind of groups they are, it's not clear. So we have some examples where these groups are surface groups, but maybe not. Maybe there are more other groups. We don't really know anything. Okay, I think I have a couple minutes left.
Yes, I have a couple of minutes.
How many?
3 minutes.
3 minutes. Okay, I will talk quickly about something called conformal dimension. So take a limit dynamical system of some contracting group. Then remember that the limit space is the quotient of the space of infinite sequences, left infinite sequences. So consider the subset of x infinity, x minus infinity, which is the set of all infinite words with a given suffix, with a given ending of length n. So these are some kind of tiles which tile our limits, our space x and minus omega, and take the images in J, in the limit space, because J is a quotient. And for a given point psi of the quotient, take all such tiles which contain psi for a given length n of the suffix, and call it t psi of n. So you have your space will be tiled by some tiles, and for a given point, you take all tiles that contain it. Tiles are closed sets, so you'll get some. It will be a neighborhood of psi. So consider AR the set of metrics for which there exists a measure on the limit space, such that these tiles are roughly round with respect to the metric. So if there are 2 radii, such that ball of radius of one radius is inside this tile and another radius contains it, and the ratio of these radii is bounded by a constant uniformly for every n and every xi. So these tiles are required to be roughly round, and the measure is what is called I-force regular. So the measure of a ball is roughly radius raised to some power. And in fact, one can show that this set of metrics is non-empty. Such metrics do exist. I will not I'll skip examples. So the definition is that Alford's regular conformal dimension of the similar group is the infimum of the Hausdorff dimensions of the matrix in this class. So this number will be a real number, a positive real number. It's not necessarily an integer. And one theorem is that the critical exponent about which I was talking about at the beginning is always less than this Alford's regular dimension, conformal dimension. The inequality is strict. For example, if you take the Grigor-2 group, the critical exponent is less than 1. The Alford's regular dimension is equal to 1. The limit space is actually a segment. And here is an example. So there are some notion of contracting groups of polynomial activities generated by automata of polynomial growth. And we proved together with Dylan Thurston and Kevin Pilgrim that in this case, the Alford's regular dimension is 1. So again, we are in this log dimension. And again, all contracting groups that were studied before are in this class. Then not only topological dimension is equal to 1, but even Alford's regular dimension is equal to 1. And here is an example of such a group. So there is so-called Hanoi Tower group. So this is the limit space, which is the Sierpinski gasket. It doesn't look like 1. Actually, the Hausdorff dimension of this is log 3 divided by log 2. However, if you change the metric like this, here's how you change the metric, and you can make the metric as close to 1 as you wish. And the theorem is that a corollary of this is that if you have a group generated by automaton of polynomial activity growth, then it is amenable. And the proof uses the fact that Alford's regular dimension is 1. Conjecturally, if this dimension is less than 2, then the group is amenable, or moreover, there is a stronger condition that is Liouville. And here is one example of such a group where dimension is 1, and so we know that the group is amenable. Okay, that's all that I want to talk about.